Hi, welcome to the session number 25, tracking session. I'm Daisuke Wei from Moscow University. I'm chairing this session, and we have 5 great papers here in this session. 3 are from TBCG journal papers and 2 are from conference papers. In the first presentation, the title of the paper is Weakly Supervised Adversarial Learning for 3D Human Pose Estimation from Point Clouds. And the presenter is Xiao Chang. Please start.
Hello, ladies and gentlemen. The topic of our report is on the 3D human pose estimation. I'm the presenter Zihao Zhang from the Institute of Computing Technology and the University of Chinese Academy of Sciences. The title of our paper is Weakly Supervised Adversarial Learning for 3D Human Pose Estimation from Point Clouds. So let's get started. Here is the outline of my presentation. As you can see, it consists of 5 parts. I will first give a brief introduction of the 3D human pose estimation problem and its relationship with virtual reality industry. Then, I will introduce the related work of our methods. Algorithm details and experiment results will be given separately then. Finally, I will draw a conclusion of our work and discuss the limitations and future works. So here is the first part, problem introduction. As we all have noticed, motion capture technology has been widely used in virtual reality and entertainment industry. For example, as the figures shown, the motion capture technology can be used to film making, such as the Siren project of Tencent and remote meeting by the Holoportation project of Microsoft. With the development of consumer devices such as depth camera, accurately estimating human pose has been the fundamental and key problem, especially from only one single camera. So, why do we focus on pose estimation problems from point clouds? Compared with RGB image-based pose estimation methods, the extra spatial information provided by utilizing the depth image for 3D skeleton extraction could yield more practical solutions. Moreover, the quality of the capture point cloud is robust under different light conditions. Therefore, we still focus on the depth image-based estimation method in this work. However, there are 3 main challenges in the problem of estimating the human pose from depth image. The first one is the self-occlusion problem. As illustrated in this picture, there could be many occluded parts if you observe the subject only in one single viewpoint, and the missing body part could make trouble in estimating the accurate human pose. The second problem is the data collection problem. It is a labor-intensive and error-prone process to manually label 3D human joints from input depths or point clouds, due to the self-occlusion between the body parts as well as tedious annotation on 3D point clouds. The third problem is data representation. Some methods project 3D point clouds to 2D depth maps and use 2D convolutional neural network, which could lose the 3D context of the point clouds. Several methods adopt 3D volume or point cloud representation. However, the network may have more parameters or lose some local information. Here are our key ideas towards these challenges. To solve the occlusion problem and handle the possible ambiguity, we adopt a discriminator network to judge whether the reconstructed human joints are plausible or not, and enforce the bone length ratios. As for the labeling problem, we observe that it is easier to construct human pose dataset with 2D human joint annotations on depth image. For example, we can label 2D human joint on depth image through a 9-color image using an off-the-shelf RGBD camera. Though 2D human joints is closely related to 3D human pose, it can only provide weak supervision of 3D human pose. Therefore, we use the weakly supervised learning method, which enables us to fully utilize both the fully labeled data and the weakly labeled data. And to address the data representation problem, we adopt a 2-stage method, which makes it possible to use the point cloud representation and the depth map representation at the same time. The experiment results shows that our method could achieve the state-of-the-art performance. Our method can be applied to different scenarios and is robust to the variance of background and gender. which could enable the use under more virtual reality scenarios. Here are some sequences showing the results under cluttered background and different gender. As you can see from these videos, our method can generate reasonable results. Now I will give introduction of three related works of our methods. The first one is a viewpoint invariant feature-based method. It presents a heat map-like 2D glimpse from a depth image and uses a recurrent network to predict the 3D pose in an iterative manner. This work treats the points in 3D space as depth maps and uses a viewpoint invariant feature to solve the occlusion problem. However, the performance of the generative 3D human pose method is largely affected by the accuracy of 2D information extraction. The second one is V2V PoseNet. It uses a 3D voxelized grid and uses a 3D convolutional neural network to estimate the per voxel likelihood for each key point. This work treats the points in 3D space as point clouds and converts it into 3D voxel grid. It uses the voxelized depth map to solve the occlusion problem. However, this method requires a clean background and is in some way time-consuming. The third one is PointNet. PointNet is a network architecture that can extract features from 3D unordered point clouds. PointNet usually takes the point coordinate and other features such as surface normals as input, which are then mapped to a higher dimensional space using a multilayer perceptron. The main limitation of PointNet is its inability to capture the local structure of the point clouds, which makes it difficult to understand the detailed spatial pattern. To solve this problem, the authors proposed a hierarchical PointNet named PointPlate++, which defines the partitioning of point clouds using the neighborhood in Euclidean space, and applies PointNet recursively to the neighborhood. Here is the third part. I will give the details of our algorithm. So here is an overview of our proposed method. As you can see, the network consists of two modules, the point clouds proposal module and the 3D pose regression module. The point clouds proposal module aims to sample the joint-related point clouds so that the computation cost is reduced and the background is removed. The 3D pose regression module aims to estimate the 3D human pose. Using the input depth map, we first estimate the 2D human pose and use it to sample and normalize the extracted point clouds from depth image. Then we use the initial 3D pose converted from the estimate 2D pose and the normalized point clouds to predict the final 3D human pose. Now I will give a detailed introduction of these two modules. The point clouds proposal module mainly consists of two steps. We first perform 2D human pose estimation using the stacked hourglass network. The loss is set as the L2 distance between the predicted heat map and the heat map generated from the ground truth 2D joint locations. The 2D human pose can be recovered by argmax operation on the predicted heat map. Notice that the argmax operation is not continuous or differentiable, so we have to train this network separately. The 2D joint detection step can guide us to get pose-aware sampled point clouds to recover the 3D human pose. We crop the bounding box of detected 2D joints from depth map, then extract local image patches centered at the detected 2D joints. Then we estimate the position of the root joint by feeding the sampled point clouds to a tiny regression network with ResNet backbone. With the root joint, the sampled point clouds can then be normalized by this formula. The 3D pose regression module aims to predict the 3D human pose through the 2D human pose and the sampled point clouds. We first obtain the initial pose by back-projecting the estimated 2D pose into 3D space and setting the depth of each joint to our estimated depth of the root joint. Then we estimate the joint of this delta Q to the initial pose. This network follows the GAN architecture and consists of the generator and the discriminator network. The generator aims to obtain the joint offsets delta Q, and the input of the generator network has a normalized point clouds. We feed the input to the hierarchical point net and obtain the joint offsets. We can update the 3D human pose by adding the joint offsets to the initial pose. The network uses the predicted 3D joint position as input and predicts whether the predicted 3D joint position is real or fake. The discriminator consists of two fully connected layers with leaky ReLU function and skip connections, and one fully connected layer with a leaky ReLU function, another fully connected layer, and a softmax function. During training, we alternatively update between discriminator D and generator G while fixing the parameters of other network. What should be noted is that during updating the generator, we use the simple yet effective indicator function to activate different loss functions based on whether the data is fully labeled or not. So here is the details of our loss function. We design a 3D post-regression network using both the fully labeled data and the weakly labeled data. The overall loss function of the generator is shown as follows, where I is the indicator function, which assesses whether the data are fully labeled data or weakly labeled data, and lambda 3D and lambda 2D are the loss weights. The variant with star means the ground truth. The first term, L3D, enforces the predicted position of the 3D joints to be close to the ground truth position of the 3D joint. We use 2D joint label supervision to learn the 3D joint location and adopt a 2D joint loss, L2D, which can reduce the searching space of the 3D human pose. It is the second term in our loss function. And to penalize illogical bone length ratios, we add a bone length ratio regularization loss to generate the 3D human pose. The bone length loss indicates that the bone length ratio computed with the predicted joints is as close as possible to the average bone length in the training dataset. The loss function of our network built upon a GAN architecture can be formulated as this. And the generator G is trained to minimize the objective function against an adversarial network D that tries to maximize it. We alternatively optimize G and D based on the min-max strategy. Here are some experiment results of our method. In our experiment, we use the ITOP dataset and Stanford EVAL dataset to evaluate our method. To evaluate the performance of our human pose estimation method, we use the following two standard metrics. The first set metrics are the percentage of correct key points, PCK, and mean average precision, MAP. The PCK value is the percentage of the detected joints out of all human joints within a given distance error threshold. The MAP is the average PCK for all human body parts. It shows the overall robustness of the pose estimation method. The other set of metrics is the mean joint error, which is defined as the mean 3D distance error of each human joint. The mean joint error can indicate the accuracy of each joint. On the right side, we show some qualitative results. The first three rows shows the results of the ITOP dataset, and the last row shows the results from the EVAL dataset. Here is the result of the cell comparison experiment. As the curve graph shows, our network design is reasonable. We also compare the performance of our methods with other state-of-the-art methods. During the comparison, we use the state-of-the-art 3D human pose estimation method, including the viewpoint invariant feature-based method, the inference embedded method, and V2V PoseNet. The comparison results are shown in this figure. Our method can achieve the state-of-the-art performance on the ITOP dataset compared with other 3D human pose estimation methods from point clouds. So here is the last part, conclusion and discussion. In this work, we aim to combine the image-based feature and point cloud-based feature and propose a weakly supervised adversarial learning method for predicting 3D human poses from point clouds. We use both the fully labeled 3D data and weakly labeled 2D data to train a robust pose estimation model. Our experiment on benchmark datasets show that our proposed method can achieve the state-of-the-art performance. Though inspiring results were obtained from this research, this work can be further improved to be an end-to-end framework. Specifically, our algorithm failed to fulfill the end-to-end prediction task due to the non-differentiable arithmetic operation in the 2D pose estimation step. Moreover, designing or utilizing other human pose representations would improve the potential of our method. For example, we can use human kinematics models with the joint angles and joint offsets and use them as the pose regression target, which could ensure that the reconstructed human joints are more plausible. That's all about my presentation. Thanks for listening.
Hey, thank you for the presentation, and we have a couple of questions here. So the first one is how to keep the estimated joint angle in a reasonable range.
As for the joint angle, we have a special loss term called the bone length ratio, which can constrain the length of the estimated bone, and it can also in some way constrain the joint angle to be in a reasonable range. Yes.
Okay. The second question is from Paulo Lima, and the question is, would it be possible to adapt your method to work with RGB input?
I think our method can also be adapted to RGB input, and as I know, the RGB can provide more information of the 2D pose, and it can in some way enhance the performance of the method, I think.
Cool. Thank you very much. Yeah, let's move on to the next presentation. Thank you. Okay, welcome back to the tracking session. The second talk is 3D hand tracking in the presence of excessive motion blur. And the presenter is Gabyong Park. Please start.
Yes, hello, I'm Gabyong Park, PhD student from KSB Lab. The presentation title is 3D hand tracking in the presence of excessive motion blur. This is joint works with Professor Antonis from University of Crete and Falls, and Juyoung Lee and Professor Untegu from KSB Lab. I'm going to introduce background of this study. As you see the figures, the hand-based interaction is useful in various applications such as virtual object manipulation and collaboration with the remote user and sign language in AR/VR. So hand tracking is very important technique to support the interaction. The many existing methods use depth camera as a sensor. So the basic goal is to estimate hand pose parameters from a depth image. The input is depth image as observation from depth camera, and the output is hand model parameters, which is used to render hand model. There are some general and interest challenges. First one is a high degree of freedoms. Hand model is usually represented in the 26 dimensions and 6 dimensions for palm and 4 dimensions for each finger. So we should estimate the hand pose parameters in the high dimensional space. Second one is self-occlusion. Because the hand object is highly articulated object, there are many cases of self-occlusions. When you see the side view of the captured image, some joints are not observed. Another challenge is similar shape. Each finger has a similar shape and length and thickness. So there are few distinct features. So existing method already successfully estimate the hand pose parameters in some situations, but our target situation is different. We introduce additional problems from fast hand motion. First one is temporal discontinuity. In the video, hand rotates fast. In this motion, the temporal continuity is broken. Actually, some existing methods have already addressed the temporal discontinuity problem using learning best approach. However, when you capture a single depth image during fast hand rotation, the depth image is severely contaminated by motion blur as the figure. Given the contaminated image, most existing methods should fail to track the hand, and it should give incorrect interaction in AR/VR. There are many related works of hand tracking algorithms. According to existing category of the hand pose estimation, we also categorize the methods into generative and discriminative and hybrid methods. The viewpoint we more focus on is two. First one is temporal discontinuity, and the second one is motion blur. The generative approaches track the hand pose parameters from rendered hand model. They assume that the hand motion is slow and smooth. For defense motion, the assumption of temporal continuity is broken, and they should fail to track the hand pose in the presence of motion blur. Discriminative approaches are able to estimate the hand pose in a single frame, so they don't have to assume that the hand should move slowly and smoothly. They more focus on the generation issue beyond the trained dataset. However, in very fast motion, the motion blur is generated. In these frames, they may fail to estimate the hand pose. Hybrid approaches combine the merits of generative and discriminative approaches. They can initialize the hand pose from detection method or learning method despite fast hand motion. So temporal discontinuity is not obstacle for these approaches. However, in the presence of motion blur, it may fail to track the hand pose. Especially in molar work, it estimates successfully hand pose and shape strong to hand interaction, but they say their limitation is motion blur in their paper. Some existing methods for hand tracking already address the general and intrinsic challenges and temporal discontinuity problem. However, to the best of our knowledge, there is no previous work to track the hand pose in the presence of motion blur. Our goal is to track hand pose parameters in the broken temporal continuity and in the motion blur using depth camera and a gyroscope. The gyroscope is attached to the back of the hand, and the depth camera captures gyroscope of one hand. Our algorithm consists of offline calibration and online sensor fusion hand tracking. We first calibrate time delay and coordinates between gyroscope and depth camera because they have different coordinates and timeline. And then we employ hierarchical particle filter for sensor fusion hand tracking. For calibration, we first estimate the pose offset between camera and gyro coordinates. As the figure, we can define two offset quaternions, O1 and O2. HCT is hand orientation from camera reference frame at time step t, and HGT is gyro pose from gyro reference frame at time step t. Next step, we define delta of HCT from initial hand orientation at time step 0. We can represent this using gyro pose and two offsets. Then we finally formulate delta of HCT and one offset O2 and delta of HG. We can reformulate this as homogeneous matrix form. Finally, we can express matrix H and vector O2. And we can estimate offset O2 with a single bell decomposition. Next, we estimate the time delay between camera and gyroscope. To do this, we repeatedly rotate the hand for a period of time with fixed translation and finger parameters. We use the depth images from depth camera and the rendered depth map from gyroscope, so we can get the optimal time delay, minimizing the sum of errors. Finally, we get pose offset and time delay between depth camera and gyroscope. Next, I'm going to explain the hierarchical particle filter for sensor fusion hand tracking. We employ the existing method from Macley's work from Pulse. In the dynamic Bayesian network, the state xmt-1 represent full hand pose parameters in the previous frame. And the states from GT0 to GTN are multiple gyro poses. Because the gyro sampling time is faster than the camera sampling time, we can get more gyro poses in a single depth frame at time step t. And S0 represents translation and rotation for palm. And the states from S1 to S5 represents the space of each finger. And the state XMT is final state for full hand pose parameters at time step t. To explain our algorithm, we should first explain observation likelihood. To do that, we define a cost function ED to calculate the error between the depth image from the depth camera and the rendered depth map from each particle. EG represents the error between the hand rotation of a particle and the calibrated gyro pose. Final cost function is a weighted sum of the ED and EG. The weight is calculated by the gyro angular velocity, which is empirically decided. We exploit the fact of the fast hand rotation generates motion blur. When motion blur is generated, the cost function should more rely on the EG. And when the motion blur is not generated, which means the slow motion, the cost function should more rely on the ED. The better formulation to detect motion blur is in feature work. So we can easily change it, the cost function to likelihood. Finally, we can calculate the weight of each sampled particle as observation likelihood. The figures show the sampled particles. We sampled 64 particles and rendered them for the observation likelihood. Because we use multiple gyro poses, we can sample the particles with slope-based sampling. For the slope-based sampling, we evenly sample the particle poses among the previous solution and the gyro poses. And then we resample the particles from the observation likelihood. Next, we one more sample the particles from the updated state S0 with a normal distribution. Because the slope-based sampling is limited to gyro trajectory, so we finely tune them one more. And then we resample particles again. And the particles for each finger are sampled from the solution in the previous frame. And we repeatedly conduct the resampling. So in this context, the finger movement relies on the previous frame hand pose parameters. So our limitation is that we don't address the best finger movement. We finally sample the particles for the full hand pose parameters from each updated auxiliary models. Then we repeat the particle filtering. We get the final hand pose parameters from average of the resampled particles. This is the experiment. We first have an ablative study. As our Bayesian method, we employ the Macley's work, and we add some components, slope-based sampling and gyro regularization. The left graph represents the percentage of frames with a fingertip error within a threshold in our self-data set. As shown in the graph, we can conclude the fusion of slope-based sampling and gyro regularization is best result. So we adopt all components for our method. This is qualitative result to show 3 consecutive frames in fast rotation. As you can see, the proposed strategy shows the best results than individually selecting each method. We observe that IR image for SR300 camera is not blurred, so the IR input is used to measure the 2D position for ground truth using a reflective marker. Next, we compare our method to state-of-the-art methods. In the frames of slow motion with temporal continuity, the OR method shows adequate accuracy, which is represented in left bar for each method. But best motion with temporal discontinuity, the performance of generative method dropped considerably. This is natural because they assume that the hand motion is slow and smooth. Our method also employ model-based tracking, so the performance drops likewise. In this sequence, the discriminative approach chance walk showed the best result because it can estimate the hand pose in a single frame. So the temporal discontinuity is not obstacle for the method. In very fast motion with motion blur, even though the discriminative method chance walk exhibited best result in the previous dataset, in this sequence, motion blur considerably affected to the method because the trained dataset does not include motion blur. Finally, our method outperformed the other method in this sequence. We release the test dataset in the link. This is qualitative comparison result. When the hand rotates fast, the motion blur is generated like this. When some joints are blurred, the performance of other methods dropped, but our method shows adequate result. And another frame is yes, like this. Yes, we have a similar result. These are some more examples for qualitative result. We observe that some parts of the finger are blurred in fast rotation, so this image artifact affects to the result of the compared method. But our method exhibits good result despite motion blur. This is a simple application in Unity 3D. The camera is attached to the HMD on user's head. We pinch the virtual object and fast rotate them. Even though the motion blur is generated by fast hand rotation, the user can interact with the virtual object. And our limitation is that we address the hand tracking in the presence of motion blur by only hand rotation. The reason is that the gyroscope can measure angular velocity of the hand rotation. Another limitation is that we assume that the camera does not move much and the hand remains within the camera's field of view. In summary, we propose the sensor fusion method to track the hand pose. As the method, we formulated it using hierarchical particle filter. In the experiment, our method exhibited accurate performance despite fast hand rotation in the presence of motion blur. Yes, this is the end of my presentation. Thank you for listening my presentation.
Okay, thank you for your talk. And if you have any questions, please put your questions on the Slido. And let me start while waiting for the questions from the audience. So I think, yeah, the method looks very nice. It works very cool, very good. And can your method handle two hands, tracking two hand motions,
Yeah.
like two hand interactions, these kind of things?
Yes, actually, this is a very hard challenges, but existing method is that I think the two hand track to track the two hand. I think we can expand our method to track but in that case, we should segment both hand. But as you said, the hand-hand interaction, I think this is very challenging. But now the present work is focused on the only one hand. So I think we should use the two-hand model. In the present work, we just use the only one-hand model. I think, yes, this is the future work. Yeah.
Okay, thanks. So the next question is from Slido. Have you tried using image-based deburring methods in order to avoid using an inertial sensor? Have you tried also using an accelerometer to also take translation into account?
Yes, yeah, image-based, yeah, we also studied in related works. Deburring method is a very good starting point, but existing deburring method is for the RGB based. Actually, the depth image, the deburring for the depth image is also studied, but they focus on the specific camera like the time of flight. I think that the blurring depends on the camera type. So yes, I think the deburring method is also future, but yeah, and accelerometer, yes, actually. Previously, we used the IMU sensor. So the IMU sensor gives the rotation, but the rotation value from the IMU sensor does not give computed value. So is why we use just gyro sensor. I think the accelerometer is very good good sensor to fuse our method. And yes, but the limitation is just we only address the only rotation. I think the accelerometer is yes good sensor to do in the future work. Yeah.
Thank
but
you very much.
we didn't try that.
Yeah, it's very interesting. Yeah. And probably this is the last question. So is there an example implementation available?
Yes.
Probably, yeah.
Source code, right? Yes, I think the implement available is yes. We list the test data set. So I said, yeah, I think the many future works, many other future works can compare their result on the data set. So I think that yes, we release the data set, but I think I will try to release the code, but I'm not sure when I finish that. So this is just future work. Yeah.
Yeah, very looking forward to it. Thank you very much.
Thank you.
Hi, welcome back. So the next talk of the tracking session is actually from my group, and I will do the presentation. And the talk is FIB AR, embedding optical fibers in 3D printed objects for active markers in dynamic projection mapping. And this work is collaboration work between Osaka University and the University of Hyogo. And I'm Daisuke Iwai, and the first author is Daiki Tone, and I'm Daisuke Iwai, and I will present it. Hi, I'm Daisuke Iwai from Osaka University. So first of all, I would like to thank you all the committee members and volunteers who work hard to make this conference happen. So in this presentation, I'm going to talk about our active marker technology for dynamic projection mapping. This is the overview of our technique. We embed optical fibers in a projection object to guide blinking light, which is emitted from LEDs attached at the bottom of the surface. The fibers and the object are jointly fabricated using a multi-material 3D printer. First, we model a projection object. The most important parts of this process are marker placement and fiber routing. Then we fabricate the object by a multi-material 3D printer. The object's pose is estimated by the captured markers, and finally we project a texture onto the surface according to the estimated pose. So previously, most motion capture systems were applied for dynamic projection mapping applications. Because multi-camera system is robust for occlusion, the projection surface shape is not restricted. The measurement area of mocap system can be large by increasing the number of cameras. On the other hand, the mocap system needs to synchronize multiple cameras, so the system becomes too complex to install in our daily environment. Another approach applies only a single camera to track a projection target, so the system becomes much simpler. These systems apply spatial patterns in representing the IDs of markers. There is a trade-off between the marker size and working range. The markers need to be large enough to be identified by a camera, so it is necessary to place a marker on a relatively planar surface to avoid occlusion. Small markers relax the restriction, but they significantly limit the working range. The trade-off of the spatial markers can be solved by applying an active marker. Active marker emits a temporal blinking pattern of infrared light to represent the marker ID. A naive implementation would be to embed LEDs in a projection object at all the marker positions. However, installing multiple LEDs and wires under the surface is tedious. And there is a unique issue of projection mapping. Markers shouldn't be noticeable to human observers when the surface is projected. The noticeable markers significantly degrade the projection mapping image quality. But all the approaches introduced before are suffered by this problem. So this paper proposes an active marker approach, which does not require manual installation works. Specifically, a user only needs to attach near-infrared LEDs at the bottom of the projection object. The infrared light from the LEDs is guided through optical fibers to the surface of the projection object. The object and the fibers are jointly printed out from a multi-material 3D printer. The aperture of an optical fiber is typically very small, so it is rarely noticeable to human observers. And the marker can be placed on a strongly curved surface. The blinking patterns can be recognized by a camera placed at a wide range of distances from markers, so the working range can be large. To reduce the number of LEDs, multiple markers are connected to the same LED, so they share the same blinking pattern. We assign two types of IDs to each marker. The first is marker ID, which is unique to each marker, shown as red. The second is pattern ID, which is same for markers connected to the same LED, shown as blue. In offline, we make a lookup table storing these IDs and the sequence of spatially adjacent pattern IDs. So for example, marker C emits the third pattern and is surrounded by markers emitting the patterns of 2, 2, 3, 1, 2. We recognize each marker from captured image sequence. So first, we measure each pattern ID from the sequence of the infrared light and the sequence of adjacent pattern IDs. Then we search the lookup table for a marker ID that has the same pattern ID and the most similar pattern ID sequence. The similarity of the pattern ID sequence is evaluated by the Levenshtein distance. This particular marker is recognized as marker B. Markers locations significantly affect the pose estimation performance, so they need to be carefully determined. So at first, we compute the suitability map for the marker locations based on the visibility from various viewing directions. Then we select points on the surface as candidate markers. The candidate markers' places hold local maximum suitability values within a predefined area. We need the restriction of the predefined area because the fiber has a certain amount of internal volume. The distance between two markers on the surface should be large enough to avoid collision of fibers. We then optimize the pattern ID assignment to the candidate markers. The objective is that the marker ID recognition robustly works for various viewing directions. We apply genetic algorithm to the optimization, where the array of pattern IDs is a chromosome. We discard candidate markers if they reduce the objective value. For more details of the optimization, please refer to the paper. The figure shows the result. In the beginning of the optimization, some markers are not recognized correctly in the simulation. After sufficient evolutions, all the markers are recognized correctly by the optimized pattern IDs. After marker locations are determined, we solve another problem, that is optical fiber routing. The optical fibers connect each infrared LED to corresponding markers, which share the same pattern ID. If the fiber routes are determined like this, there are several problems, such as a part of a very small curvature radius causing significant loss of infrared light, a part locating outside the object, and a collision between fibers transmitting different blinking patterns. So we carefully design the fibers to solve these problems to obtain the optimal fiber routing. We use a multi-material 3D printer that can print an object using transparent material. This is the structure of our optical fiber. We apply the clear and support materials as the core and cladding of our optical fiber, respectively. To avoid crosstalk of infrared light leaked from fibers inside an object, we cover the fibers with a thin black layer. We cover the object surface with a thin white layer to increase both light diffusion of infrared light and the invisibility of the markers for human observers. The thickness of the materials are determined through several trials and errors. For the route optimization, at first it is necessary to know the light throughput of the fiber. The light throughput is dependent on the length and curvature of the fiber based on Lambert-Beer law. We printed fibers with different lengths and curvatures and measured their light throughputs. Considering the use of fibers for active markers, we characterize the throughput as the longest distance between the end of a fiber and the camera, where the emitted blinking pattern of infrared light can be detected. The measurements are fitted to our model based on the Lambert-Beer law, and for more details, please refer to the paper. Finally, the fiber route is optimized by minimizing this objective. The first term works to increase the light throughput. The second term works to increase the distance from each fiber to the surface. The third term works to increase the distance between fibers transmitting different blinking patterns. The last term is a regularizer. These are the examples of our marker placement and fiber routing results for 3 different objects. The colored lines represent the fibers, and fibers with the same color are connected to the same LED. we can confirm that the fibers of different pattern IDs did not collide with each other, and all the fibers were placed inside the object. In particular, in the bunny object, fibers were successfully routed through the narrow neck. The 3D models are then fabricated from a multi-material 3D printer. We prepared 7 small holes in the bottom surfaces of the objects as LED sockets. The same hole layout was shared among the objects, so that the same base component consisting of an electrical circuit, battery, and LEDs is reusable. So the video shows projected results on 2 different objects, bunny and building. So we can confirm that the textures are mapped correctly when the objects move and even when they are occluded by hand. So this is the result of the bunny object. So when the object is covered by a hand, large part of the object is covered by the hand, texture is still robustly mapped onto the object. And this is the result of the building object. So it can track relatively large volume, and it also tracks the rotation. And again, the object can be covered by hand like this. So we evaluated how accurately our system can estimate the pose of a projection object to check the tracking range. As a result, the system could estimate the position of each object with a small error relative to the translation distance, whose range was 1 meter in our experiment. So we confirmed that the system works in a relatively large tracking range. We checked how robust the system works under occlusion. When an object is occluded, the number of markers captured by the camera becomes smaller. If the number becomes lower than 4, then the system cannot estimate the pose of the object based on solving the PNP problem. In this experiment, we covered more than half area of the object. In such a tough situation, the system could capture more than 4 markers and robustly estimate the pose of the object. So we confirm that the system is robust for occlusion. And this is the summary of my presentation. So we propose an active marker technology for dynamic projection mapping, and the technical contributions are, there are 2 technical contributions. One is marker placement optimization, and the second one is fiber route optimization. And interesting future directions are to use more transparent material, which is very recently available, and to apply this technology to a flexible object such as a soft robot. I hope our framework will be applied in many fields in near future. Thank you. Okay. Sorry. Yeah, I'm gonna start. I mean, I am chair and I'm the presenter, so I'm doing the Q&A session by myself. So there are some questions in a Slido. So the first one, do you also propose a method which will automatically provide fiber optic network design if a 3D model is given? Yeah, actually this is what we did in this paper. The optical fiber network is actually automatically designed from our algorithm once a 3D object is given. And the second question is, if you have other light sources in the room, static light or flashing light sources, will that interfere with the tracking? Yes, it interferes. It does, but actually we applied M sequence pattern as the blinking light pattern, which has a good characteristics that it is a better, how can I say, performance in the it is not interfered very much. And yeah. And the last question is how much latency is introduced by the use of temporal markers? Oh, yeah. So at the moment we use, sorry, I forgot the exact number, but I think we used maybe 9 or maybe less than 10 binary patterns for representing the ID of each marker. And we use 500 Hertz camera, which means that I think it works in 50. No, I mean, it works in 500 Hertz, but once we lost the object, then we have to wait for like 10 frames to, recover the binary information. Okay, so these are all the questions, and that's it. Thank you very much. Hi, so welcome back to our tracking session. The next paper is SPLAT, Spherical Localization and Tracking in Large Spaces. And this work is done by University of Otago and California Polytechnic State University group. And Luis Baker will present this work. Please start.
Everyone, I'm Lewis Baker from University of Otago, and I'll be presenting SPLAT, Spherical Localization and Tracking in Large Spaces. I'd just like to acknowledge my co-authors, Jonathan from Cal Poly, and my PhD supervisors, Stephanie, Stephen, and Tobias from Otago. The main motivation behind this work stems from the fact that, in many augmented reality applications, the users are stationary and performing mostly rotational movement. And this is especially true in the case of mobile augmented reality, which is currently very popular. Common methods for tracking camera motion which support these applications typically rely on mapping the environment. For example, simultaneous localization and mapping, or SLAM-based approaches. These kinds of methods can become unstable in large environments when the amount of translational movement is small when compared to the size of the environment. Some examples of this kind of situation include augmented sports spectator applications such as Zollman et al., panorama generation such as Wagner et al., and could extend to seated office scenarios and outdoor tourist attractions. In 2016, Jonathan Ventura introduced spherical motion and provided methods for computing relative pose with spherical motion for the purposes of offline structure from motion, or 3D reconstruction. Spherical motion is essentially a constrained form of camera pose in which the camera's translation vector t is fixed. For example, 001 for an inward-facing camera or 00-1 for an outward-facing camera. The rotation matrix is unconstrained, but fixing t results in the camera's center being constrained to move along the surface of an imaginary sphere, with its optical axis pointing in the direction of the sphere's normal. The main idea here is that spherical motion is an approximation of how people move their mobile devices when capturing or exploring their environment. In terms of tracking for augmented reality, our goal is to determine the camera's position and orientation in real time, Two common approaches to this would be SLAM and rotation-based tracking. In the figure on the right here, this is a screenshot from my experiments with OrbSlam. We can see a camera in blue moving through an environment and simultaneously generating a map or point cloud of what it can see. In rotation-based tracking, we assume that there is no translation at all and that the camera is purely rotating around its center. This approach is another approximation of the true motion, which is usually sufficient when the environment is large enough. And so some limitations of the SLAM-based approaches. As I mentioned earlier, the small translational baselines can lead to bad initializations of the map, which usually results in tracking failure. And as the size of the space gets larger, the amount of translation required to reliably initialize the map also increases. Finally, while many SLAM approaches are running in real time, the tracking process is still a significant chunk of computation, so finding ways to improve computational efficiency is also important. So moving on to our approach, we propose SPLAT, a keyframe-based SLAM system that's similar to state-of-the-art, but with the following differences. So all the components of the system incorporate a spherical constraint. So this tracking system specifically targets the applications where the user is mostly rotating. We propose a new keyframe data structure, which leverages the spherical constraint to simplify the keyframe selection process. And we detail a new solution for computing absolute pose with a spherical constraint. And we show that our system has improved tracking rate compared to state-of-the-art methods. An overview of how the SPLAT system looks like. There are three main components. So in yellow on the left, we have initialization, which happens first. In this stage, the objective of the system is to initialize some 3D points in a map off which we can track the camera. In the final step of the initialization, we create our keyframe sphere, which is the keyframe data structure, which I'll explain later on. And the two other components, tracking and mapping, are running in two separate threads concurrently. The tracking thread runs in real time and computes the camera pose for each frame of input video. And the mapping thread takes the tracking information and creates new map points as the camera explores the environment. So in some more detail with the initialization component, our first step is to extract features. In our case, we follow suit with the state-of-the-art and use orb features. We then apply standard feature tracking methods to determine how the orb features are moving in the image as the camera moves around. And the feature tracks are these white lines that you can see in the animation here once it restarts. So these white lines here, and they turn pink once the initialization is completed. So then using the feature tracks, we can compute the relative pose with a spherical constraint using the method from Ventura 2016. And to initialize the 3D points, we triangulate them using the feature tracks or 2D correspondences and the relative pose that we previously computed. Finally, once the map is initialized, we set up our keyframe data structure. So the keyframe sphere is our new method for determining for a given tracked frame whether or not it has a unique enough view to become a keyframe. In unconstrained keyframe SLAM systems, this process can be quite difficult as it's not possible to tell if a camera is looking at a new part of the environment using its position alone. However, with a spherical constraint, the camera's viewing direction is always parallel with the normal of the sphere, so it's much easier to determine if the camera is observing unseen parts of the environment. In a spherical tracking system, you can think of the sphere's surface as the space of all possible camera poses. So in our implementation, we quantize the space by generating anchor points as uniformly as we can across the sphere's surface, which are these black points that you can see in the figure here. And as the camera moves, and the blue line here is the camera's trajectory, keyframes are created and assigned to the nearby anchors as depicted by the red points. So this is basically how our keyframe selection process works, using the anchors to help with selection, and this naturally enforces an upper bound on the number of keyframes allowed by the system as well. And so moving on to the tracking component, In some ways, it's similar to the initialization component in that we continue to apply the feature tracking, but we need to take care to keep track of the origin of the feature tracks and which 3D map points they correspond with. We also create new feature tracks for newly detected orb features, and these new tracks are triangulated later by the mapping thread. And the final step in the tracking is to actually compute the pose for the current frame, which we do using our spherically constrained perspective 2-point method, which is detailed in the following slides. So to compute the camera pose for a given image, we require a set of 3D points, which come from our mapping thread, and their corresponding 2D positions from the tracking. We want to compute our rotation matrix R, given that we know the translation vector T, which is our spherical constraint. Our first step is to compute the lambdas, or the depth values, that can be used to unproject the 2D points to 3D points in the camera's coordinate system. So if we have those lambdas, we can construct a second 3D point set, which can be aligned to the first using absolute orientation method of Horn to give us the rotation matrix. And to actually compute those lambdas, we use the fact that we know that the scale of the world in camera coordinate systems is the same. So the distance between any two pair of points in the world coordinate system should be the same as the distance between the corresponding pair of points in the camera coordinate system. So you can set up these two equations here, and that requires 3 2D to 3D correspondences. But in the case of spherical motion, there is one correspondence that always exists, and that is that the origin point of the world is always directly behind the camera, and so that must always project to the center of the image. So to solve these equations, we only really need 2 correspondences from the SLAM system itself. Finally, we have our mapping process. Once a frame is tracked and flagged by the keyframe sphere to become a keyframe, we begin by matching this frame to the neighboring keyframes, which is kind of a simple form of loop closure that can boost the observations of the map points that already exist. Then we simply update the keyframe sphere by flagging its anchor as occupied. We then triangulate new map points for the 2D tracks. Finally, we perform bundle adjustment, also enforcing the spherical constraint by fixing the translation vector in the optimization. So that's overall how the splat system works. For more detail, please see our paper. Now onto our results. We started with synthetic tests to try to determine how the different tracking methods perform in environments of varying sizes. So to do this, we simulated a camera moving in a circle inside a 3D modeling program. So we're using Blender. And the camera is always moving in a circle of radius 1. So that's this orange circle that you can see here. We also generate a textured sphere surrounding the camera with this high resolution image of a church. And we vary the size of this textured sphere to simulate environments of different sizes. We compared SPLAT to OrbSLAM 2, which is a state-of-the-art SLAM system, and also a simple rotation-based or homography-based tracker. So these are our synthetic results. On the y-axis, we have tracking rate, which is the longest successive run of tracked frames divided by the total number of frames. For our simple homography tracker, we also include a more forgiving metric, since it's fundamentally a simpler system that just performs homography estimation frame to frame, which is this orange line that you can see here. So for OrbSLAM, results were initially good with space radius up to 5 multiples of the camera radius. At around radius 15, it became consistently unreliable and would lose tracking shortly after initializing. The homography tracker performed worse with the small space size and got better as the space size increased as expected. And our system, SPLAT, was able to track reliably with all of the tested sphere radii. We also did some real tests with 10 different video sequences. All the videos were captured from mobile devices, and we have a mixture of indoor and outdoor and portrait and landscape orientations. For this experiment, we wanted to know how reliable the tracking methods are with real data from stationary users. And for this experiment, we just compared SPLAT with OrbSLAM. And in these results, we show tracking timelines. So red represents an untracked frame and blue represents a successfully tracked frame. In general, Splat tracked very reliably, with one exceptional case here, Stadium 1, in which our system took longer to initialize. But once initialized, tracking was stable. OrbSlam results were a bit more patchy. In some cases, it tracked very well, such as the indoor lab sequence and two of the larger environment sequences, so Field and Stadium 1. Many of the large outdoor sequences tracked poorly, such as the outdoor river scenes and the courtyard scene. Overall, we're able to show that Splat is able to track reliably in many cases, utilizing the spherical constraint for pose estimation. We also completed some experiments on the tracking accuracy of Splat, but due to the lack of datasets containing spherical motion, it is difficult to attain ground truth and reference trajectories for this. In this experiment, however, we compared OrbSlam and Splat to a reference trajectory from an Intel T265 tracking camera. We found that overall, OrbSlam and Splat had relatively similar absolute trajectory error, but there were no significant differences there, while Splat had a small but significant improvement in relative pose error in some of the cases. However, in future, we would like to do more tests on the tracking accuracy, perhaps with higher quality ground truth, as the Intel tracking camera itself is not ground truth and is actually itself prone to error and drift. So in summary, we've shown that a keyframe sphere data structure can be used to effectively manage keyframes utilizing a spherical constraint. Splat provides a new solution to the absolute pose problem that incorporates a spherical constraint as well. Through synthetic tests, we showed that tracking is reliable in spaces of varying sizes. In our real tests, we showed that tracking is also reliable in many outdoor environments. We presented some initial results on accuracy, but in future we plan to focus more on acquiring reliable ground truth and reference trajectories in order to perform more extensive evaluation in this area.
Can you tell us when we start?
So finally, thank you for your attention, and I'd like to acknowledge and thank all the people and organizations involved in this project. Thank you very much.
Okay, thank you. Okay, so Luis, we have a couple of questions on Slido. So let me take one. Do you think this approach can work with drones, given that translation is solved by GPS coordinates?
Yeah, I think it could be applied to drones, especially if they were hovering around sort of a fixed position. I think you could also use the GPS positioning for like a global localization, which would that would also be definitely helpful for augmented reality applications. So yeah.
Okay. The second question is, could Splat be used together with traditional keyframe-based SLAM to handle both rotation and translation changes? How Splat compares to panorama tracking methods?
Yeah, so for the first part, I think there have been other tracking methods which combine rotation-based trackers and general SLAM systems, and they've been shown to work quite effectively. So I think, yeah, for future work, we could maybe extend it to be kind of like a hybrid system, which would be possibly be able to switch between the spherical tracking and general tracking, and how it compares to panorama tracking methods. So yeah, in our evaluation, we did a comparison to a basic homography-based or rotation-based tracker. We found that our method was reliable when it was tracking in spaces of pretty much all sizes, whereas with the pure rotation methods, at least in the synthetic test, we showed that they were failing when the environment was very close to the camera and the camera's moving in a circle. So the translation component kind of creates, or it kind of messes with the assumption that the camera is purely rotating.
Good. So the last question, how is the radius of the sphere set? And the camera can only move within the sphere, so map size is limited.
So the sphere that the camera is moving on is that sphere is always radius 1. So that's kind of where the spherical constraint comes from. So the translation vector is always 0, 0, 1. And so the camera can't actually move inside the sphere. It's always moving around the outside of the surface and looking outwards. So since we don't know what the user's actual radius is of their motion, the scale of the map that we're creating has an unknown scale.
So how can it be, how can it be defined from the true sphere, like the ellipsoid movement is acceptable?
Yeah. So in the real tests that we did, we weren't too careful to create perfect circular motion. So we weren't moving it on like a fixed rotational arm or anything. It was just kind of holding a mobile phone out and moving it around like this. So it does support some deviations, but we haven't done any thorough experiments with how far you can deviate. But that's something for future work.
Okay, thank you very much.
Thanks.
Okay, welcome back to the last paper presentation of the tracking session. The last paper is Deep Soft Procrustes for markerless volumetric sensor alignment. And the presenter is Alexandros. Please start.
Hello, my name is Alexandros Doumanoglu. I am from Center for Research and Technology, Hellas, Information Technologies Institute. And I'm going to present you our work, Deep Soft Procrustes for markerless volumetric sensor alignment. First, let's start with volumetric video. Volumetric video is a new emerging type of multimedia with the main benefit that it allows free viewpoint spectating. It can be displayed in 2D devices, in 3D displays, even in VR goggles. It is the next logical step after stereoscopic productions and 360 video, as it allows it combines visual quality of photography with the immersiveness and the interactiveness of spatialized content. It is a key enabler for performance capture, and in order to acquire volumetric video, we need specialized setups called volumetric capture setups, which are a special case of multi-view capturing setups. Here is Panoptic Studio, a state-of-the-art volumetric capture studio. It is comprised of more than 100 RGB and IR sensors. It has about 10 RGBD sensors, However, this system is expensive, it is complex, and non-portable. Another example is holoportation, which has pairs of RGB IR, and again, it is expensive, complex, and hardly to move. Our lab has contributed to the community with a volumetric capturing system, which is low cost, flexible, and portable. It uses commodity grade RGBD sensors. That's why it is cheap. It is simple because it offers a simple tool chain to work with, and it is portable because all of its components are portable, sensors, mini PCs, tripods, etc. Regardless of the sensor setup or the application, spatial sensor alignment is required. Spatial sensor alignment is the process of taking the measurement of each viewpoint and bringing all of them in the same coordinate system. When we talk about spatial sensor alignment, there are some things that is nice to have, something like simplicity for those users that do not have the technical knowledge to understand technical details. It needs to be portable if the volumetric capturing system it supports is a portable one. It needs to be cost efficient because if it has to have a cost that is proportional to the cost of the volumetric capture system. And if the volumetric capture system is portable, usually portable systems are less costly. Typically, marker-based calibration is established by 2D visual correspondence in multiple views, the classic checkerboard pattern, or using other markers like Aruko. Each of these methods, the checkerboard pattern exploits the geometry and the visual patterns, the geometry of the checkerboard, and the Aruko marker would exploit the visual marker with a corresponding depth measurement. These methods are robust under varying lighting conditions. However, they are prone to human error, and they too much rely on human intervention. There are some technical details that have to be pointed out when using those methods. For example, in the checkerboard case, there may be captures that the checkerboard is not correctly detected between views. Or in Aruko, we may have markers that are not correctly placed on the corresponding landmark. In any case, both those cases are prone to error accumulation in multiple camera setups because they establish pair correspondence between views. Another category of calibration methods is structural calibration based calibration methods with markers. They establish 3D correspondences between a landmark denoted by a marker and the corresponding known landmark in the visual structure. An example is Octolith, which is able to calibrate over 100 RGB IR sensors. Another example is Alexiadis et al. It's a structure which is also employs QR markers in order to facilitate key point detection and then perform correspondence estimation with a virtual model. Another case could be the same as Alexiadis, but instead of QR codes using Aruko markers. These methods exploit prior knowledge of the geometric structure. There is no error accumulation across multiple camera setups, and it requires assembly of a structure, precise placement of markers, and a virtual model of the structure. One step ahead of this is to use markerless structure-based calibration. Again, a 3D structure, but without the markers. We exploit these methods exploit the known 3D geometry of a physical structure to establish key point correspondence with its virtual structure. It was first introduced by Papachristou et al., whose method relied on asymmetric 3D structure. They trained a neural network in order to segment depth maps of the containing captures of the structure, and then extracting key points on the centroids of the sites in order to perform key point correspondence establishment with the virtual structure. There is no error accumulation in these methods. They exploit prior knowledge, and they have minimum human intervention, which is their most impactful benefit. However, they still need to assemble a structure to have a virtual model. And in the specific case of this related work, the method, the spatial alignment method, was strictly to work towards 4 diagonal views at a 90 degrees angle interval. Our work aims to overcome these limitations in the unrestricted sensor count and support unrestricted sensor placements. We aim for simplicity, as we do not want to have users to be technically knowledgeable in order to use the method. We want to support portable systems, so our method must be portable, and we want it to be cost-effective in order to be easily adopted. So, similar to Papachristos, we employ a structure composed of 4 standard packaging boxes. These boxes are commercially available and can be assembled in an asymmetric structure, which is easy to assemble. Of course, the whole structure is portable, since it is comprised of small components which can be easily ported here and there. It will serve as an anchor. The structure itself will serve as an anchor to register partial views. Okay, first of all, in our method, we do structure labeling. We semantically annotate the structure's planar sides. Then we use the pipeline for incidence is something like that. We first capture the depth map. Then we pass the depth map to a neural network which does semantic segmentation. And then we establish key point correspondences with the virtual structure. We perform the calibration between the key points, and finally we have a calibrated point cloud. How we train the network? First of all, we need some data generation, and because we have the virtual model of the structure, we generate synthetic views of the structure and obtain depth maps and label maps with from random viewpoints. Then we do network prediction. Our network employs soft attention that we'll explain later. And then the optimization of the network is driven by 2 types of losses. The one is standard cross-entropy loss for segmentation, and the 3T loss, which we call the soft Procrustes loss. I will explain this further later. So just to break our training process step by step. First, we need to sample camera poses around the volume surrounding the virtual structure. So first we do that. We sample camera poses. Then we render the virtual structure from these poses and obtain depth maps and label maps, ground truth label maps. Then, in order to accommodate for inconsistencies between synthetic and real data, we augment with holes our depth maps. Holes are there in order to simulate no depth measurements in the depth map, like untextured areas in stereo technology or absorptive or reflective material in type of light technology. We augment further with noise. We add 2 types of noise, one targeting devices, simulating devices that use the time of flight technology, and other types of noise, disparity noise, which targets noise coming from devices, sensors that use stereo technology. We augment our synthetic render view with a background from a dataset or with some Gaussian some noise pattern, like Gaussian noise or uniform noise. And finally, in some of our examples, we do erosion in our depth maps in order to account for erroneous measurements at the edges. So here are some example augmentations that we have. Our network is a standard unit with skip connections, and it has a soft attention. The soft attention module localizes the structure. It is self-supervised with a ground truth mask generated from synthetic data, and it is end-to-end trainable. Now the soft Procrustes loss, for the soft Procrustes loss, all the pixels contribute in short terms, all the pixels contribute to the 3D coordinates with their 3D coordinates to all the key points by their probability of belonging to each key points class. And finally, we do the correspondence with the virtual structure and do standard Procrustes in order to obtain the 3D loss, which is a standard L2 loss. Why do we do this? Why do we have soft Procrustes? Well, soft Procrustes bridges the 2D segmentation task with the 3D pose estimation one. It produces segmentations whose centroid key point is better candidate to be used as a correspondence. And it has proven to improve camera pose estimation accuracy when training the network in a larger space of possible sensor poses. Here we see some qualitative results. These are taken, these are acquired depth maps are with Intel Reason sensor. And here it is with Azure Kinect. So it is the same network. Our network is invariant and robust across different sensor types. Here are some qualitative calibration results of the acquired structure after the calibration step. We compare against the marker-based method. The idea is simple. We have the structure and we attach Aruco markers on the centroids of each side of each box. And then we sample the depth map and then use these key points as correspondences with the virtual structure. So now here we can see error maps between the calibrated, the aligned point cloud of our method after our method has run and the virtual structure. Warm colors indicate lower errors, while hottest errors indicate higher errors. You can see in this example that our work is comparable with the marker-based one, while our work remains markerless. Here is another example where our work managed to converge better than Papachristos one. You can see in the middle that Papachristos has failed to converge, while our work worked without problems. So finally, in conclusion, we present the multi-sensor calibration method that has no restriction on number of sensors of the volumetric capturing setup. It requires minimum user involvement. It is low cost. It is sensor agnostic and achieves same or better results with state-of-the-art methods overcoming their drawbacks. Thank you.
Thank you. So, okay, the questions. So at the moment we have no question on the Slido. So let me start while waiting for the questions from the audience. So you used colored boxes for the alignment. Is it correct?
You said colored?
Colored boxes.
Standard boxes, yes. Packaging boxes, yes.
Yeah. Okay. So the placement of the boxes. So you do the placement of boxes. Can we place the boxes like arbitrarily place the boxes?
No. You need to place the boxes. You need to place the boxes in a specific configuration. But it is there is a very simple rule to follow, and you can do it with ease. Let me show you. Yeah, like that. You see, the boxes are follow a specific pattern in order to place them. Each box is rotated with respect to each bottom one about 90 degrees to the left.
I understand.
So yes, there needs to be a specific pattern in the placement of the boxes.
I see. Okay, so there is a question from the audience. So how fast this method works and how much time it takes to set up?
Okay. At the inference time, it's really fast. A few seconds and you are done. And we don't have optimized code right now, but it's almost instantaneous.
Mm-hmm. I see. Okay, so thank you very much.
Thank you.
So this is the last. This is the end of the session, and actually, the presenters will be in hubs. Probably some of the presenters will dive into the hubs. So please go to the VR sessions after this session in the break time, and for the detailed discussions, and where the place where the information of the hubs room will be announced via Slack. Thank you very much.